Hello students, the topic that we are going to discuss today is moving charges and magnetism, NCERT section 4.3 to 4.4 and example 4.3 to 4.4. So this is the disclaimer. Learning objectives. So to describe the motion of charged particles in a uniform magnetic field, we are going to calculate the radius of circular or helical path followed by charged particle. We are going to analyze how the direction of magnetic fields affects the particle's trajectory. We are going to apply the Biot-Savart law to calculate magnetic fields created by current carrying conductor. We are going to understand the vector nature of magnetic fields and how the right hand rule relates to current direction and field direction. So the topics that we are going to cover today is NCERT section 4.3 motion in a magnetic field, example 4.3, NCERT section 4.4 magnetic field due to current element Biot-Savart law, and example 4.4. So the topic NCERT section 4.3 motion in a magnetic field. So charged particle following specific path in uniform magnetic field. So this is the figure 4.5 and figure 4.6. In figure 4.5 there is a circular path of charged particle, and in figure 4.6 there is a helical motion. Okay, so we are going to discuss these two type of motions of charged particle in uniform magnetic field. So let's consider detailed motion of charge in a magnetic field. Okay, in yesterday's lecture we only discussed about the parallel or anti-parallel, or how force is applying on the charged particle moving in a magnetic field in generalized term. Now we will consider the detailed motion of a charged particle in magnetic field. From mechanics, we know that force does work when it has component along the direction of particle motion. Okay, only work is done, because what is work done? Equal to F dot D, means force dot product of force and displacement. Okay, if there is a component of force along the displacement, then there will be work done. If there is no component of force along the displacement, then the work done is zero. Okay, from mechanics we know that force does work when it has a component along the direction of particle motion. In a magnetic field, the force acts perpendicular to the particle's velocity. Okay, so we have discussed in previous lecture that magnetic force always act perpendicular to velocity and magnetic field, because magnetic force is given by Q V cross B. Okay, so resultant of V cross B will be in the direction perpendicular to both velocity of the charged particle and magnetic field in that region. Since there is no component of force along the velocity, okay, since we know that magnetic force is perpendicular to both velocity and magnetic field, so since it has no component along the velocity, it is perpendicular to the velocity, so it has no component, force has no component along velocity, so it will not change the velocity. Okay, so if it is not changing the velocity, kinetic energy remains conserved. That means no work is done according to work energy theorem. What is work energy theorem? Work is equal to change in kinetic energy. If there is no component of force along the velocity, it means velocity is not changing. That means kinetic energy is remaining constant. And if kinetic energy is constant, that means no work is done. That is zero change in kinetic energy of particle. Hence magnitude of velocity remains unchanged, though direction of velocity may change. Okay, only magnitude of velocity remains unchanged. Direction can change. Like we can see that in circular motion, if particle is moving in uniform circular motion, magnitude of velocity will be constant, but direction is changing at every instant. So magnetic force differs from electric force. How? electric force QE can have parallel or anti-parallel components to direction of velocity of particle. Okay, so QE, force, electric force equal to QE, can have parallel or anti-parallel components. Okay, because we know that in electric field, if there is a positive charge, it will move in the direction of electric field. If there is a negative charge, it will move in the opposite direction to the electric field. So force is acting parallel or anti-parallel. Okay, so electric force QE can have parallel or anti-parallel components along the velocity of particle. Okay, but magnetic force only have perpendicular component to the velocity of particle. So in electric force, in the case of electric force, work is done by the electric force and energy is transferred to the particle because velocity of the particle is changing. If it is moving parallel to if there is a positive charge and it is moving in the direction of electric field, then it will experience force in the direction of electric field, its velocity will increase. If there is a electron moving in the direction of electric field, it will experience force in the opposite direction of electric field and its velocity will decrease. Okay, so velocity is changing due to this QE force, and work is done by electric force and energy is transferred to the particle. Transferred energy will appear as change in kinetic energy of the particle. Okay, so this transfer of energy can be seen as change in the kinetic energy or change in the velocity of the particle. So now charge particle following circular path in uniform magnetic field. Okay, we will learn about circular and helical step by step or one by one. Firstly, we will discuss about circular path. So for a uniform magnetic field, what is uniform magnetic field? Means at any point or at every point in the region, magnetic field value is same. Okay, magnitude of magnetic field at every point and direction also is same in the region. So for uniform magnetic field B, when velocity V is perpendicular to B, if velocity V is perpendicular to magnetic field B. Okay, so how velocity is, you can see in the diagram. Okay, in this diagram you can see velocity is in this plane of paper, or we can say plane of screen. Okay, so velocity is in this plane of paper, but this magnetic field, these cross signs, what that means? That magnetic field is perpendicular to the plane of paper and directed inwards. Its direction is inwards and perpendicular to the plane of paper, and velocity is in the plane of paper. That means magnetic field B and velocity V, they always have angle between them is 90 degree in this condition, because magnetic field remain perpendicular to the plane of paper and velocity is in the plane of paper. So there so for the movement of particle, their angle, the angle between velocity and magnetic field will always remain 90 degree. Okay, for uniform magnetic field B, when velocity V is perpendicular to B, the perpendicular magnetic force Q V cross B act as centripetal force. Okay, in this condition, the magnetic force, that is Q V cross B, will act as centripetal force. Okay, you can find the direction of force at any instant by right hand rule. Okay, point the fingers of your hand towards velocity. Okay, point the fingers in the direction of velocity and curl them towards magnetic field, means curve them towards inwards, in the direction inwards, perpendicular to the plane of paper. Okay, and you will see the direction of thumb, your thumb will give the direction of force, which is upward in this case for this Q charge in the below part of circle. Okay, or at this part, rightmost part, if velocity is in upward direction, you have to point your fingers in the direction of velocity and curl them toward inside, toward inwards, perpendicular to the plane in the direction of magnetic field. You will get the direction of thumb as in the left direction. Okay, in this case. Similarly, for any point in the circle, you can find the direction of force. So you will see that force is directed towards the center of the circle. Okay, and acting as centripetal force. So what does centripetal force do? It will provide necessary force to complete it is the condition for circular motion. This centripetal force results in circular motion. Okay, for circular motion, centripetal force is required. So this centripetal force requires in circular motion perpendicular to the magnetic field. Okay, circular motion will be in plane of paper, and magnetic field is perpendicular to the plane of paper, and direction is direction is going into the paper. Okay, so the centripetal force results in circular motion that is perpendicular to the magnetic field. So direction of magnetic force at any point on the circular path can be found using screw rule or right hand rule. Okay, you can find the direction of force at any point on the circular path by using right hand rule, as I have mentioned earlier. Now, charge particle following a helical path in uniform magnetic field. So this is a helical path. How this path is formed? If velocity is not perpendicular to magnetic field. Okay, so magnetic field is in direction x direction. You can see in the diagram 4.6. Magnetic field is in positive x axis along. So magnetic field is along positive x axis, and this velocity v is not perpendicular to this b. It is at some angle. It is at some angle to this b. Okay, so we will resolve this velocity into two components. One component is perpendicular component, other component is parallel component. That parallel component is along this parallel component is along the magnetic field. Okay, and we know that if the charge particle is moving along the magnetic field, then it will experience no force. That means velocity of particle will not change. So this v parallel is along the magnetic field. So this v parallel will not change. Okay, this v perpendicular is perpendicular to this b. So this will change. Okay, due to this v perpendicular, motion of the particle is circular. Due to this v parallel, motion of the particle is linear. So due to the combination of both circular motion and linear motion, the resultant path is helical motion. Okay, it will form helical motion. It is moving linearly, also following circular motion, the combination of two motions. So if velocity has a component along b, okay, so I have explained, if the velocity is perpendicular to b in circular motion case, then there is no component of velocity along the b. Now velocity is at some angle. So there are two components of velocity, one is along b and one is perpendicular to the b. And if velocity has a component along b, these components remain unchanged, because velocity doesn't change when particle is moving in the direction or opposite to the direction of magnetic field. So since magnetic force on charge particle is perpendicular to magnetic field, then component of velocity along b remains unchanged, while perpendicular component of velocity produces the circular motion. Due to the combination of both linear motion is due to parallel component of velocity. Okay, so due to the combination of both linear and circular motion, charge particle will follow helical motion, as shown in the figure 4.6. Now again coming to circular path, charge particle following circular path in uniform magnetic field. For circular motion, the centripetal force is given by, if any particle is following circular motion, then the centripetal force is given by Fc equal to mv square by r. Okay, where m is the mass of the particle following circular path of radius r and velocity v. When velocity is perpendicular to magnetic field, the magnetic force acts as centripetal force. Okay, when there is a perpendicular component of velocity to the magnetic field, then circular motion is being followed. Okay, so the magnetic force is acting as centripetal force, which results in circular path. So magnitude of magnetic force is given by, what is the magnetic force? Fm is equal to q v cross b, and we are taking only magnitude here, not direction. Direction we can find at any instant using right hand rule. Okay, as shown in the figure also. We can find at any point by using right hand rule for vector products. So here magnitude of this magnetic force is Fm equal to q v cross b, q v b sine theta, and theta here is 90 degree because velocity has direction perpendicular to magnetic field. Magnetic field is directed towards inside. Okay, perpendicular to the plane of paper and inside. Direction of magnetic field is perpendicular to the plane of paper and inside, and direction of velocity is in the plane of paper, so both are perpendicular. So sine 90 degrees 1, so magnetic force is qvb. Theta is equal to 90 degree because v and b are perpendicular to each other, equating both centripetal force and magnetic force, because centripetal force is being provided by magnetic force. So equating both, so mv square by r is equal to qvb. Okay, so after rearranging these things, we have to find the radius r. We have to find the radius of this circular motion or circular path or circle. So the radius of circular path followed by charged particle is given by r equal to mv by qb. After rearranging that equation, we can find radius. Radius is equal to mv by qb. Mark it as 4.5 equation. Okay, so now you can see radius r increases. Radius is depending upon mass of the particle, velocity of the particle, charge of the particle, and magnetic field. Okay, the radius r increases with increase in momentum mv. If mv means momentum, this is linear momentum mv. So if mv is increasing, that means radius will also increase, because radius is directly proportional to mv, directly proportional to linear momentum. The radius r decreases with increase in the magnetic field. If we increase the amount of the magnetic field in that region, then radius will decrease, because radius is inversely proportional to magnetic field. So if omega is the angular frequency, or we can say angular velocity also. Okay, omega is called angular velocity, and it is also called as angular frequency, not simple frequency. That is linear frequency, nu. This is angular frequency, that is omega, and it is also named as angular velocity. So angular frequency is, then we know that v equal to omega r. Okay, these expressions or formulae you have seen in circular motion in 11th class. So v equal to omega r. So putting the value of r in above equation, so the expression equation 4.5 and expression of radius we are going to put here in v equal to omega r. So we will get omega equal to, also we know that omega is equal to 2 pi nu. Nu is the linear frequency, omega is the angular frequency. So relation between frequency and angular frequency is omega is equal to 2 pi nu, which is equal to, after putting the value of radius in v equal to omega r, we got qb by m. So omega is qb by m. Okay, so mark it as 4.6a equation, where nu is frequency of rotation. Now you can see this angular frequency is independent of velocity of the particle, also radius of the circular path. It is only dependent upon charge, magnetic field, and mass of the particle, not dependent upon velocity of the particle. So nu and omega are independent. So both frequency and angular frequency are independent of velocity v of the charged particle. Okay, we can also write the expression for nu here. How? Dividing the 2 pi with qb by m. Okay, so 2 pi will go there. It will become qb by 2 pi m. So nu will be qb by 2 pi m and omega will be qb by m. So both are independent of velocity v of the charged particle. The independence of frequency nu from velocity has important application in the design of cyclotron. Okay, a device called cyclotron, which is used for accelerate the charges to a high speed, very high speed. Okay, so that independence of frequency nu from the velocity has important application in that device in the design of cyclotron. The time period of the revolution is given by, so we have to calculate the time period, which is time period and angular frequency is related as t equal to 2 pi by omega, equal to 2 pi upon 2 omega is 2 pi nu. So 2 pi and 2 pi will get cancelled. Time period will be equal to 1 by nu. So time period is reciprocal of frequency. So now charged particle following helical path in the uniform magnetic field. Okay, now we will see how helical path is being formed. Okay, I have also mentioned it, how it is forming, because velocity is not perpendicular to magnetic field here. Velocity is at some angle to the magnetic field other than 90 degree. So this velocity, we will going to resolve the velocity in v perpendicular and v parallel. Okay, so this v perpendicular is perpendicular to this b, due to which circular motion is being followed, and this v parallel will result in linear motion. Due to combination of both the motions, the resultant motion of charged particle will be helical. Okay, so if there is a component of velocity parallel to the magnetic field that is denoted by v parallel, it will make the particle move along the field. If the charged particle then will be helical. Okay, so the path of charged particle then will be helical. It is not perfectly circular. So you can see in 4.6 also. So pitch, the new term that we are going to define here. What is pitch? Distance moved along the field in one rotation. Okay, you may have seen pitch of screw gauge. Okay, in 11th class, pitch of screw gauge. What is pitch? Pitch means distance moved by any instrument, anything that is rotating or that is following circular motion and linear motion simultaneously. Okay, so like screw, it has helical structure in screw. If we are rotating the screw, that helical structure will move in the circular path as well as in the linear direction. Okay, so that is pitch, that distance moved along the field in one rotation. So distance moved by this charged particle in the direction of field. It means linear distance traveled by the charged particle in one rotation. It is completing one rotation along this. It is moving from here, and after completing one rotation, after reaching here. Now, initial position and final is different, separated by some distance. So this linear distance traveled in one rotation is called pitch. Okay, so this pitch p, distance moved along the field in one rotation, is given by, so pitch is given by, that is linear distance traveled. That linear distance is due to v parallel. Okay, so the responsible for this linear distance is v parallel. So this pitch is v parallel into the time period to complete one circular motion. So v parallel into time period. Pitch is the distance, simply distance, that is moved in one rotation. So the time taken by the one rotation multiplied by velocity, parallel velocity. So it will give the pitch. So 2 pi m, what is t? 2 pi m by qb. So p will be equal to v parallel t equal to 2 pi m v parallel upon qb. Put the value of t, and t is equal to 1 by nu. Okay, so we know the value of nu, we can find the value of t, and we can put here, find the pitch. So this is 4.6b. The radius of the circular component of motion is called radius of helix. Okay, so the circular component, the radius of the circular component in this helical motion is called the radius of the helix. Now, example 4.3. What is the radius of the path of an electron, mass 9 into 10 to the power minus 31 kg and charge 1.6 into 10 to the power minus 19 coulomb, moving at a speed of 3 into 10 to the power 7 meter per second in a magnetic field 6 into 10 to the power minus 4 Tesla perpendicular to it? What is its frequency? Calculate its energy in kilo electron volt. Okay, 1 electron volt is given by 1.6 into 10 to the power minus 19 joule. So you have to list all the things that is given in the question first. Then what is to be found? Radius of the path. Second, frequency and energy in kilo electron volt. And 1 electron volt is given. What is kilo electron volt? 1000 electron volt. Okay, so if 1 electron volt is 1.6 into 10 to the power minus 19 joule, then 1 kilo electron volt is multiplied by 1000. So 1.6 into 10 to the power minus 16 joule. Got it? Now let's see the solution. So you have to list all the given things. So mass of the electron is given, m equal to 9 into 10 to the power minus 31 kg. Charge on electron E is given by 1.6 into 10 to the power minus 19 coulomb. Speed of electron is given, v equal to 10 to the power 3 into 10 to the power 7 meter per second. Magnetic field, B equal to 6 into 10 to the power minus 4 Tesla. Now what we have to find? Firstly, radius. So using equation 4.5, radius of circular path is given by, what was the expression? mv by qb. So put the value of m, that is 9 to 10 to the power minus 31. Put the value of velocity 3 into 10 to the power 7. Put the value of charge, that is 1.6 into 10 to the power minus 19. And put the value of magnetic field, that is 6 into 10 to the power minus 4 Tesla. So R, after solving, R is equal to 27 into 10 to the power minus 24 upon 9.6 into 10 to the power minus 23. So after solving further, R is equal to 2.8125 into 10 to the power minus 1 meter. So R is approximately equal to 28 into 10 to the power minus 2 meter. And approximately equal to 28 centimeter. So 10 to the power minus 2 meter is centimeter. So R is approximately equal to 28 centimeter. Now we have to calculate the frequency. So what is the frequency? 1 by t. So what is t? Time period. That is, time is equal to distance upon velocity or displacement upon velocity. We can say distance upon velocity in circular motion, because displacement for one revolution is 0. So we can say distance covered in one revolution upon velocity. That is the time period of circular motion. So v equal to nu equal to, that is frequency, equal to 1 by t, equal to, what is t? Distance covered in one revolution, that is 2 pi r upon velocity. Okay, so t is in denominator, so it will become v upon 2 pi r. So put the values of v, which is 3 into 10 to the power 7 upon 2 pi into 2.8125 into 10 to the power minus 1, which will result in 117 into 10 to the power 6 per second. And this second inverse is known as hertz. Unit of frequency is hertz. So nu equal to 17 into 10 to the power 6 hertz. And nu is equal to 17 10 to the power 6 hertz is known as megahertz. Okay, now we can calculate the energy of the electron. Okay, electron will have kinetic energy. Okay, so due to magnetic force. So kinetic energy will be half mv square equal to half into 9 into 10 to the power minus 31 kg into 9 into 10 to the power 14 meter square per second square. Velocity is given 3 into 10 to the power 7. So after squaring it, it will become 9 into 10 to the power 14 and unit will become meter square per second square. So after solving, E equal to half 81 into 10 to the power minus 17 kg meter square per second square. Kg meter square per second square is known as joule. So energy is equal to 40.5 into 10 to the power minus 17 joule. So it is approximately equal to 4 into 10 to the power minus 16 joule. Now 1 kilo electron volt is equal to 1.6 into 10 to the power minus 16 joule, as I have mentioned when I started the question. So energy in kilowatt is given by E equal to 4 into 10 to the power minus 6 joule upon 1.6 into 10 to the power minus 16. So it will result in kilo electron volt. So energy in kilo electron volt is 2.5 kilo electron volt. Got it? Now our next topic is NCERT section 4.4, magnetic field due to current element, Biot-Savart's law. So relation between current and magnetic field it produces. So figure 4.7, what it is representing? Illustration of Biot-Savart law. The current element I produces a magnetic field dB at a distance r. So magnetic field we know arises from currents. Okay, so we have discussed that moving charges in Oersted. What Oersted observed that moving charges or currents produce magnetic fields. So magnetic field we know arises from currents, moving charges, and the other thing that from that magnetic fields arises is magnetic moments, similar to dipole moments, electric dipole moments, similar to that magnetic moments, which we are going to discuss in next chapter, magnetism and matter. So magnetic fields can arise from magnetic moments of particles present within the material. Okay, we'll discuss in next chapter. In this chapter we are only focusing on the magnetic fields produced by currents or moving charges. Relation for magnetic field at point in space due to current carrying conductor is given by Biot-Savart's law. Okay, so what is the magnetic field at a point in space is produced by some conductor that is carrying current? That relation is given by Biot-Savart's law. So what was that relation? There is a finite conductor XY. Okay, so you can see in figure 4.7, there is a conductor finite. It is not infinite, it is finite conductor XY. Okay, carrying current I in the upward direction, you can see. Consider a very small element dl of the conductor. Okay, you have to consider a very small element. They have considered in the diagram also where IDL is written. Where IDL is written, this arrow, this blue color arrow in the upward direction is small element dl and its direction is same as current. Okay, so this small element, consider small element dl of the conductor. Let us take a point P at distance r. So you have to take a point, consider a point in the space which is at a distance r from this element. From this element, this point is at a distance r from the element dl. The magnetic field dB at due to this small element dl at point P is to be determined. We have to find the magnetic field at this point P due to this small element dl. Okay, firstly we have to find the magnetic field dB due to this small element, then after we will integrate it. Okay, so then there are special cases of Biot-Savart's law for a straight conductor, for a circular loop, for an arc. Okay, then we are going to integrate all the small elements on the conductor. Okay, but in generalized term, in generalized formula, we are going to derive for dB due to this small element dl. So the magnetic field dB due to small element dl at a point P is to be determined. Let theta be the angle between dl, that dl. dl is point at this point. dl is in that direction. This blue color arrow is showing the direction of dl. So this theta angle is between dl and this displacement vector r. So this is the theta. This dashed line is representing the direction of dl or alignment of dl, and this arrow in the upward direction is showing the direction of dl. So between this dl and this r vector, position vector, or we can say displacement vector. So between this dl and this displacement vector, that is theta angle. Okay, so now we have seen the diagram. Now according to Biot-Savart's law, the magnitude of magnetic field dB at this P point is given as, it is directly proportional to current I. So this magnetic field dB is directly proportional to current flowing through that conductor. Okay, it is directly proportional to I. If current is more, that dB will be more. Okay, and it is also directly proportional to element dl. If we take large element dl, then the magnetic field will be large. If we are taking very small dl, then the magnetic field will be very small. So, and this magnetic field dB is inversely proportional to the square of distance r. So this distance from this dl to this P point, r distance. Okay, so it is inversely proportional to the square of this r distance. In vector notation, now what we have seen, according to Biot-Savart's law, magnetic field dB is directly proportional to current as well as element dl, element length, and inversely proportional to the square of distance r. But in vector notation, okay, its representation is somewhat different. But in magnitude, you are going to understand that how it is directly proportional, how it is inversely proportional. In vector notation, its representation is somewhat different. So in vector notation, magnetic field dB at point P is represented by dB is proportional to I dl cross r upon r cube. Now you may have questioned that it is inversely proportional to square of distance r. Then why it is written cube of distance r? Because it is in vector form. When we do this cross product dl into r, it will result in dl r sine theta. Okay, then this r and this r cube, this one r is cancelled with this one r. Then there in denominator r square will be left with us. Okay, when we find this resultant of this cross product. But it is in vector form, so that's why there r cube is there. In scalar form or without vector magnitude, then there is r square. We are going to see the magnitude of dB also. This is vector form. So dB is proportional to I dl cross r upon r cube. Now we have to remove this proportionality sign. So after removing the proportionality, we are left with dB equal to, this is the constant of proportionality, mu naught upon 4 pi I dl cross r upon r cube. Mark it as 4.7a equation. So this is the constant of proportionality, mu naught upon 4 pi. So magnetic field direction is perpendicular to the plane containing dl and r. Now what is the direction of this magnetic field? We can find using again right hand rule, and it is perpendicular to both dl and r. And how we can find? Align your fingers in the direction of dl and curl them in the direction of displacement vector r. You will get the direction of magnetic field at point P. Okay, so at point P, align the fingers at point P, align the fingers in the direction of dl and curl them towards r. Okay, you will get that direction of dB is, your thumb is pointing perpendicular to the plane and inwards. Okay, so dB is at point P is directed towards perpendicular to the plane and inwards, and cross is marked. That means magnetic field is in inside direction and perpendicular to plane. Okay, you can find the direction using right hand rule for vector products. So you can see here now. So direction of dl cross r is also given by right hand rule. So look at the plane containing vector dl and r. What is the plane of dl and r? It is plane of paper. Imagine curling your fingers from dl vector towards r vector. if the movement of fingers is anti-clockwise, if movement of your fingers is anti-clockwise, the resultant is directed towards you. Okay, but in this diagram, movement of fingers is in clockwise or anti-clockwise? It is in clockwise direction. So the resultant is directed away from you. That means inside, directed inwards. Okay. So magnitude of magnetic field is, now we will see the magnitude. You can see dl cross r, it will become dl r sine theta, and one r will cancel with r cube. Okay, so it will result in r square. So magnitude of this dB is equal to mu naught by 4 pi I dl sine theta upon r square. Mark it as 4.7 B. Now you can see this dB is proportional to current I and also proportional to current element dl and inversely proportional to square of distance r. So we have used the result of cross product here. The value of constant of proportionality, that constant of proportionality mu naught upon 4 pi in SI units is given as 10⁻⁻⁷ Tesla meter per ampere. Okay, so that is the constant of proportionality and that is its value 10⁻⁷, and its unit is, we can find using this above equation 4.7b. Okay, if we are rearranging this equation, and it will become dB r square upon I dl sine theta. So dB unit of magnetic field Tesla, r square meter square upon ampere meter, and meter will cancel out 1 meter from meter square, then it will become Tesla meter per ampere. So mu naught upon 4 pi is equal to 10⁻⁷ Tesla meter per ampere, and mark it as equation 4.7c, where mu naught is the permeability of free space. Okay, it is similar to, it is somewhat identical to epsilon naught, that was permittivity of free space, but mu naught is permeability of free space. What is permeability? What was permittivity? Epsilon naught. Permittivity is the measure of easiness of penetration of electric field lines through any material. Okay, and this is replace the electric field lines with magnetic field lines. Permeability of free space or permeability of any material is defined as the measure of how easily material is allowing the magnetic field lines to pass through it. So the Biot-Savart law shares some similarities and differences with Coulomb law. Okay, so there are some similarities between Biot-Savart law and Coulomb's law, and there are some differences. Let us see. So what are the similarities? Both laws are long range forces with inverse square dependence. Okay, both laws are inverse square laws, means they are inversely proportional to square of distance r, and they are long range forces, not short range. Both laws follow superposition principle. Okay, you know the superposition principle. Okay, what is superposition principle? Electric field at any point can be represented as vector sum of all the electric field lines due to individual charges present around any point. Okay, and what is superposition principle for this magnetic field? Magnetic field at point P can be represented by the vector sum of all the magnetic field lines produced by individual small elements dl. Okay, so both laws follow superposition principle. So what are the differences? Electrostatic field has scalar source, that is charge. Electrostatic field is produced by scalar source, charge, but this magnetic field is produced by vector source, that is dl, idl. So what is idl? It is a vector. It has direction, same as current. Another difference, electrostatic field is along the displacement vector r. So electrostatic field is represented in the direction of r, along the displacement vector, but magnetic field is perpendicular to the plane of displacement vector r and current dl. Got it? Electrostatic field is in the direction of displacement vector. Okay, we can represent the electric field direction by r cap, that is along the displacement vector r. But here magnetic field is perpendicular to the plane and displacement vector r, and also perpendicular to the current element dl. Magnetic field has angle dependence. In the formula of magnitude of magnetic field, we have seen that it is depending upon sine theta. It has angle dependence. But in electric field, there is no angle in its expression. So electric field doesn't involve any angle in the expression. So it is angle independent. Now, magnetic field at any point in the direction of dl, the dashed line. Okay, you can see the dashed line. So magnetic field at any point in the direction of dl. This dashed line is direction of dl, and it is direction is towards upward direction. So magnetic field at any point in the direction of dl, the dashed line is 0. Why 0? Because along this line theta is 0. If any point is lying on this line, dashed line, then theta will be 0. That means sine theta is 0, due to which from equation 4.7a dB will become 0. So at this line, dashed line in the diagram, theta is 0, due to which magnetic field at this line is 0. We can say along the dl vector, magnetic field is 0. So the relationship between permittivity epsilon naught, permeability mu naught, and speed of light c is. So there is a relation between all three variables, that is epsilon naught, mu naught equal to, so product of epsilon naught and mu naught. So you can multiply it with 4 pi and divide it by 4 pi. So it will become 4 pi epsilon naught and mu naught upon 4 pi. So 4 pi epsilon naught, value of 4 pi epsilon naught is, value of 1 by 4 pi epsilon naught is 9 into 10 raised power 9. So it is 4 pi epsilon naught. So 9 into 10 raised power 9 will go in denominator. And mu naught by 4 pi, value of this 10 raised power minus 7. After solving it, it will become 3 into 10 raised power 8 whole square. And what is 3 into 10 raised power 8? C, speed of light. So can we say epsilon naught mu naught is equal to 1 by c square? So product of epsilon naught and mu naught is equal to 1 by c square. So since the speed of light in vacuum is constant, the product epsilon naught and mu naught is fixed in magnitude also. So this is the relation. This relation will be used in your 8th chapter, electromagnetic waves. Okay. So now example 4.4, an element delta L equal to delta X I cap. I cap is the direction of this delta L. Is placed at origin and carries a large current I equal to 10 ampere. What is the magnetic field on the y-axis at a distance 0.5 meter and delta x is 1 centimeter? You can see the figure 4.8. There is a small element delta x and delta L is delta x is magnitude and I cap is direction. I cap means in the positive x direction. And 0.5 meter, you have to find the magnetic field at y-axis at a distance of 0.5 meter. So it will become r equal to 0.5 meter and current is given. So let's see the solution. So what is given? dl equal to delta x equal to 10 raised power minus 2 meter. It is given. I is given 10 ampere. R is given 0.5 meter. And mu naught by 4 pi, we know that this is constant. Its value is 10 raised power minus 7 Tesla meter per ampere. And theta is also given. Theta between r and dl vector. Dl vector is in x axis, is towards x axis. And that r is directed towards y axis. So angle is 90 degree. So sine 90 is 1. Now you can put the values in the formula. So magnetic field is given by dB equal to mu naught by 4 pi I dl sine theta by r square. Equation 4.7b. Now put all the values and find the dB. So dB is equal to 10 raised power minus 7 into 10 into 10 raised power minus 2 upon 25 into 10 raised power minus 2. So dB is 0.4 into 10 raised power minus 7. And the final answer is 4 into 10 to the power minus 8 Tesla. This is the value of magnetic field at point P. Now what is its direction? So direction of the field is in the positive Z direction. You can find the direction using right hand rule. Point the fingers in the X direction, curl them towards Y. You can see your thumb will point towards U. Okay, so it is positive Z direction. In outward direction there is positive Z axis. In inward direction there is negative Z axis. So this is so since you can also find the direction by using this properties of vector products. So dl cross r, dl is in I cap, r is directed towards j cap. So delta x I cap into y j cap equal to y delta x I cross j. What is I cross j? K cap. So y delta x k cap. So its direction is positive z axis. So we remind you of the following cyclic properties of cross products that you may have seen in the 11th class. So I cross j is k cap, j cross k is I cap, and k cross I is j cap. Okay, what is I cap? Unit vector of x axis. What is j cap? Unit vector of y axis. What is k cap? Unit vector of z axis. Okay, note that the field is small in magnitude because it is due to small element. So cyclotron frequency Vc represent the frequency of a circular motion of a charged particle in a uniform magnetic field given by the formula Vc equal to qb by 2 pi m. Okay, let's have a quick recap of the topics that we have discussed today. So what is cyclotron frequency? The frequency of circular motion of a charged particle in uniform magnetic field. That is represented by qb upon 2 pi m, where q is charge, b is magnetic field strength, and m is mass. Cyclotron frequency remains constant regardless of the particle speed. What is cyclotron frequency? Perpendicular velocity to the magnetic field. So it remains constant regardless of particle speed or orbital radius. The Biot-Savart law describe how current carrying elements create magnetic field expressed as dB equal to mu naught by 4 pi IDL cross R upon R square, where dB is the magnetic field element, I is current, dl is length element, and r is distance. The total magnetic field at any point P must be calculated by integrating the Biot-Savart equation over the entire current carrying conductor. Okay, let's you can solve yourself. These are some practice questions you have to solve yourself for your practice. A proton enters a uniform magnetic field of 0.5 Tesla with the velocity of 2 into 10 to the power 6 meter per second perpendicular to the field. You have to calculate A, the radius of the circular path, B, the time period of the motion. And given mass of the proton 1.67 into 10 to the power minus 27 kg and charge is 1.76 into 10 to the power minus 19 coulomb. Second question. An electron moves with a velocity of 3 into 10 to the power 6 meter per second at an angle of 30 degree with a uniform magnetic speed of 2 Tesla. Find the pitch of the helical path and second, the radius of the helix. Third question. How does the magnetic field vary with the distance from a long straight conductor according to Biot-Savart law? And the fourth question. Why does a charged particle follow helical path when it enters a magnetic field at an angle? Okay, there are two conceptual questions, two numericals. You have to try yourself. Okay, we are going to do the DPP section. Okay, you can see first question. A charged particle moves in a uniform magnetic field. Okay, you have to do the DPP with me or you can solve afterwards. A charged particle moves in a uniform magnetic field with velocity perpendicular to the field. What quantity remains constant? Momentum, velocity, acceleration, or kinetic energy? Okay. Okay, someone is saying kinetic energy. So the radius of circular path of the charged particle in a magnetic field is given by Okay, someone is saying second option. The frequency of a charged particle circular motion in a magnetic field depends upon velocity and magnetic field, mass and charge, magnetic field and charge to mass ratio, or radius and velocity. Okay, someone is saying third option. If a charged particle velocity has a component parallel to the magnetic field, its path is circular, parabolic, helical, linear. Okay, someone is saying fourth option. An electron moves in a magnetic field of 6 into 10 to the power -4 with speed this. What is the radius? So it will take time. I will marking random late. Okay. So let's see. Fourth question is incorrect. Okay. If a charged particle velocity has a component parallel to magnetic field, its path is linear. So its path will be helical. Okay.